more extensive intermolecular hydrogen bonding which is present in carboxylic acid. It is having more boiling point than corresponding aldehydes, ketones, aldehydes which is having comparable molecular mass. If electron withdrawing groups are present, the electron richness will become less, and what happens, the carboxyl group becomes more reactive. What is the acid present in vinegar? It is ethanoic acid or acetic acid, right? Hexanoic acid is used in the manufacture of nylon 6,6. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry. So today I am back with the last session of the chapter Aldehydes, Ketones and Carboxylic acid. So in the last session we started with carboxylic acids, right? That is the last part of the chapter, and we discussed the nomenclature and as well as the methods of preparation of carboxylic acid. So in today's session we are going to see the physical properties and chemical properties of carboxylic acid, right? So beginning with the physical properties. So aliphatic means without ring structures, that is straight chain or branched ones, right? So aliphatic carboxylic acids up to 9 carbon atoms are colorless liquids. They are liquids, okay, at room temperature with unpleasant odors. So up to C9, that is C1 to C9 carbons, that is carboxylic acid containing 1 carbon atom to 9 carbon atoms. They are generally present as liquids and they have an unpleasant odor. The higher acids are wax-like solids and are particularly odorless due to their low volatility. So if you have to get the odor or the smell, means it must be volatile, right? It must be able to evaporate. But the higher ones, that is carboxylic acids having the number of carbon atoms above 9, they are solids and they will be less volatile, right? Carboxylic acid have higher boiling liquids than aldehydes, ketones and even alcohols of comparable molecular mass. So they are higher boiling points. They have higher boiling points. Now why it is that is? It is due to more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. So because of more extensive intermolecular hydrogen bonding which is present in carboxylic acid, it is having more boiling point than corresponding aldehydes, ketones, aldehydes which is having comparable molecular mass. The hydrogen bonds are not broken completely even in the vapor phase. In fact, most carboxylic acid exist as dimer in the vapor phase or in the aprotic solvent. So they exist as dimer. So as I told you, they have the ability to form hydrogen bonds because of the carboxyl group present. They can form hydrogen bonds. And even in the vapor phase means once it evaporates, what should happen? The hydrogen bonds should break. But even if it is in the vapor phase, the hydrogen bonds is not breaking. That means what? Of course, the bond is really strong, right? So you can see here RCOOH, that is one carboxylic acid group, and another one you are having RCOOH, right? So as you can see here, from one carboxylic acid molecule, oxygen having negative charge, hydrogen having positive charge, here positive, here negative. So there will be an intermolecular, that is between two different molecules, there is a hydrogen bond which is formed. So in vapor phase also this bond will not be broken. That is why it is having higher boiling points. So carboxylic acid is the one which is having the highest boiling point. So remember that. Clear. Now, simple aliphatic carboxylic acids having up to 4 carbon atoms are miscible in water due to the formation of hydrogen bonds. Again, why any organic compound is able to, they are soluble in water is because of the formation of hydrogen bond. So just now we discussed here also, that is it is able to form hydrogen bonds with other molecules of carboxylic acid. Same way it is able to form hydrogen bonds with water as well, right? Okay, so that is why they are generally soluble, but those are only the carboxylic acid having lesser number of carbon atoms. The higher carboxylic acids are practically insoluble in water. So the higher one, more and more carbon atoms are there, means of course it will be insoluble in water because of this alkyl or aryl group is hydrophobic in nature. Now due to the increased hydrophobic interaction of hydrocarbon part, that is why they are less soluble. Benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water. So what is benzoic acid? This is benzoic acid, right? So of course aryl group is there. That means of course it is going to be insoluble in cold water. Carboxylic acids are also soluble in less polar organic solvents like benzene, ether, alcohol, chloroform. So they may not be soluble in water, but they are soluble in polar organic solvents like chloroform, benzene, etc. Clear? Moving on to the chemical properties of carboxylic acid. So first we are going to study the reactions involving the cleavage of oxygen-hydrogen bond. That means we have RCOOH, right? So first we are going to discuss about the breakage of this bond, that is oxygen-hydrogen bond in the carboxyl group, right? So acidity, the carboxylic acids evolve hydrogen with electropositive metals and form salts with alkalis. They react with weaker bases such as carbonates and hydrogen carbonates to evolve carbon dioxide. So because of this acidic nature means what? It is able to donate its H+. So as discussed, oxygen-hydrogen bond is going to break, so H+ is going to be released. So what is going to happen is when carboxylic acid reacts with highly electropositive metals like sodium, potassium, etc., it will release hydrogen, that is hydrogen gas, H2 will be released. Now if it is reacting with alkalis, it will form salts. Okay, that is, for example, sodium hydroxide, if it is reacting, it will form sodium salt of that carboxylic acid. Salts will be formed. Now, if it is reacting with weaker bases, right, like carbonates or hydrogen carbonates, it will evolve carbon dioxide. Okay, so let's see. This reaction is used to detect the presence of carboxyl group in an organic compound. So these reactions, if hydrogen is evolved or carbon dioxide is formed, or else the salt of carboxylic acid is formed, we can confirm the presence of carboxylic group. So in identification of functional group experiment in lab also we have done this. When carboxylic acid or the organic solvent which is given to you is made to react with sodium bicarbonate, carbon dioxide gas will be evolved. You can see effervescence. So that is how we confirm the presence of carboxylic acid, right? So let's see. This is 2 moles of carboxylic acid reacts with sodium, that is an highly electropositive metal. What will happen? You will get the sodium salt of carboxylic acid and hydrogen gas will be evolved. Clear? Now, carboxylic acid can also react with a base, strong base like sodium hydroxide. You will get the sodium salt of the carboxylic acid again and water, right? So sodium salt of carboxylic acid will be formed. Now again carboxylic acid reacts with sodium bicarbonate. So what will happen? This hydrogen is going to be replaced by the sodium. So you will get again sodium salt of carboxylic acid. Then you have one H here and one oxygen together forms water. And what else will be there? CO2 will be there. Carbon dioxide will be liberated. Now carboxylic acid dissociate in water to give resonance stabilized carboxylate anions and hydrogen ion. So this is your carboxylic acid RCOOH. In water, what will happen? It will dissociate into carboxylate ion, that is RCOO minus, right? RCOOH in presence of water, it will form carboxylate ion which will show resonance. As you can see, RC double bond O. And what will happen? Because of this electronegativity difference here, the shared pair of electrons will move towards oxygen and oxygen will get a negative charge. So again what can happen? There will be lone pair of electrons on the other oxygen. That can form a double bond here. So there can be a resonance which there can be a resonance effect which acts between these two oxygen atoms. So that is what is shown here. That is RC, and you have these 3 bonds and it is shown like this. That means it can happen, that is with this oxygen atom or this oxygen atom, the resonance can take place. So from this above reaction that we have discussed, that is this one, that is carboxylic acid, when it reacts with water, it forms hydronium ion. This is H3O plus hydronium ion and the carboxylate ion. So using this equation, we are going to write the equilibrium equation. So we have already studied this in class 11. So equilibrium constant can be written as the product of molar concentration of the products raised to their powers divided by the product of molar concentration of the reactants. So what are the products here? Carboxylate ion and the hydronium ion. So the molar concentration of H3O plus into RCOO minus, that is a carboxylate ion, divided by, what is the reactants here? Carboxylic acid and water. So it will be molar concentration of water and carboxylic acid ion. Now we are taking water to the other side, to the numerator. So what happens? K equilibrium into water you will get. What is that? That is equilibrium constant of acid, right? Ka, which is equal to product of molar concentration of hydronium ion and carboxylate ion divided by the molar concentration of the carboxylic acid. So where K equilibrium is equilibrium constant and Ka is the acid dissociation constant. For convenience, the strength of an acid is generally indicated by pKa. Okay, value rather than its Ka value. So how is pKa and Ka related? pKa is equal to minus log of Ka. As you can see here, it is minus log of Ka. So once from the equilibrium equation, equilibrium constant equation, we can calculate Ka. What it is? Dissociation constant of an acid. Once that is calculated using this equation, we can calculate the pKa value of an acid, from which we can tell how strong or weak the acid is. So smaller the pKa value, stronger will be the acid, the better it is as a proton donor. Strong acids have pKa value less than 1. So what you have to remember, stronger acids will have high Ka value and very low pKa value. So if the pKa value is less than 1, we can say that the acids are very strong. Moderately strong acids have pKa values between 1 and 5, and weak acids will have pKa value between 5 and 15. The pKa value will be very high. Extremely weak acids will have it more than 15. Carboxylic acid are amongst the most acidic organic compounds. So carboxylic acids of course will have the pKa value less than 1. Moving on to the next one. Carboxylic acids have higher acidity compared to phenol. Now if you are comparing phenols, phenols are also acidic. We have discussed this in the alcohols, phenols and ethers chapter. Now coming to carboxylic acid, if you are comparing carboxylic acids and phenols, carboxylic acids are more acidic. Why is that? So this is an important question. Reason: the negative charge in carboxylate ion is delocalized over 2 electronegative oxygen atom. So you can see it is RCO. minus. This is the carboxylate ion. So just now we have already discussed the resonating structures. So because of the electronegativity difference, this can come here. So what will happen? You will get a negative charge over here, and this negative charge can come as a bond here. So what is the other resonating structure you can get? It will be RCO minus and double bond O here. So it can either come there or here. The resonating structures will happen between 2 oxygen atoms in carboxylate ion, right? Whereas it is less effectively delocalized in the phenoxide ion between 1 oxygen atom and a less electronegative carbon atom. In phenoxide ion, what is phenoxide ion? This is phenoxide ion, right? So the resonance is happening between this oxygen atom and the carbon atom which is present here. So comparing these two, you have 2 oxygen atoms between which the resonance is taking place, which are both more electronegative. Here you have it between 1 oxygen and 1 carbon, which is less electronegative. So comparing these two, of course, carboxylate ion will be more acidic, right? So thus the carboxylate ion is more stabilized than phenoxide ion. So carboxylic acids are more acidic than phenols. So more the resonating structures, more it will be stable. So that is why carboxylic acid is more stable, hence they will be more acidic. Clear? Moving on to the next one, effects of substituents on acidity of carboxylic acid. So carboxylic acids are COOH, the general formula, and if there are any other substituents also present, right? For example, if an electron withdrawing group is present or if an electron donating group is present, what will happen to the acidity of this carboxylic acid? Let's see. So electron withdrawing groups, okay, that is they take up electrons from the carboxyl group, increases the acidity of carboxylic acids by stabilizing the conjugate base through delocalization of negative charge by inductive and resonance effect. So electron withdrawing group means already the carboxyl group is electron rich because of the presence of 2 oxygen atoms. So electron withdrawing groups will take up the extra electrons from the carboxyl group. So what happens? The carboxyl group will be more available for reactions, right? It will be more reactive in that case. So if electron withdrawing groups are present, the electron richness will become less, and what happens? The carboxyl group becomes more reactive. Clear? Now, conversely, electron donating groups decrease the acidity by destabilizing the conjugate base. So, electron donating groups, it will give extra electrons to the carboxyl group, which will make it much more deactive or less reactive, right? So, electron withdrawing group stabilizes the carboxylate anion and strengthens the acid. So, if electron withdrawing groups are present, the acid will become more stronger, or else the acidity will become more. If electron donating groups are present, the acidic character will become less. Electron withdrawing groups like nitro groups are present means more and more it will be acidic. Electron donating groups like alkyl groups, more alkyl groups are present means of course the acidity will decrease. Clear? Now, the order of the effect of groups in increasing acidity is, so you have phenyl, which is least acidic. Then you have the halogens, that is iodine, bromine, chlorine, fluorine, and then you have cyano, Cn minus, then you have nitro, then you have CF3. So comparing all this itself, you can see here all of these are electron donating groups, right? And you have the electron withdrawing groups like nitro, CF3, all of towards the end. So if you have the nitro or cyano groups present in your carboxylic acid, they will be more acidic. So this is the order. Thus the following acids are arranged in the order of decreasing acidity based on their pKa pKa value, that is in the decreasing order. So this is the order: CF3COH having the highest acidity, then CCl3COH, CHCl2COH, NO2, nitro comes, right? Nitro will be electron withdrawing, so it is more acidic. Then you have NC, that is cyano group is there, CH2COOH. Then you have FCH2COH, ClCH3COH, bromine carboxylic acid is there. Then you have formic acid, ClCH2CH2COH is there. Then you have benzoic acid. Then C6H5CH2COH, CH3COH, that is acetic acid. Then you have propanoic acid, all of that. Clear? So more alkyl groups are present means, see, you can see that comes in the end. Alkyl groups are electron donating, so they are least acidic compared to the ones having halogens or nitro groups. Clear? Now, the direct attachment of groups such as phenyl or vinyl to the carboxylic acid increases the acidity of corresponding carboxylic acid due to the resonance effect. So, directly vinyl group or phenyl group. Now, what is vinyl group? As you can see here, CH2 double bond CH, and the functional group is directly attached to the carbon atom, which is part of a double bond. So, that is called as vinyl. So, you can see what happens. This double bond also can donate its electrons towards the carbon atom, and more resonance will be there. Hence, more acidity. Here also what happens here? So, here is the next resonance structure which is shown here, and this bond can come back to here. See, in the first structure, you can see this double bond is shifted here. So, what happens? As the carbon is losing its electron, carbon will get a positive charge, which is shown here. Now, this can come back here also. And here also what is happening? The oxygen can move here. And from this oxygen, which is lone pair is present, this can move here also. So, resonance, more resonance will take place. Hence, more acidity will be present. Now, this is because of greater electronegativity of sp2 hybridized carbon to which carboxyl carbon is attached. The presence of electron withdrawing group upon the phenyl of aromatic carboxylic acid increases their acidity, while electron donating groups decreases their acidity. In aromatic carboxylic acids also the same thing happens. If electron withdrawing groups are present, acidity will increase. Electron donating groups are present, acidity will decrease. So, let's consider here, this is benzoic acid, simplest one. Then you have 4-methoxy benzoic acid. That is, on the 4th carbon, you have a methyl group which is present, and you have nitro also. So, comparing these three, which one will have the highest acidity? We ourselves can predict. So, you have an alkyl group which is electron donating. This is electron donating. Here, you don't have any other substituents. And nitro is electron withdrawing. So, we just studied now electron withdrawing and donating. If you are comparing, electron withdrawing will give you more acidity. So, this will be the order of acidity. So, because of that, nitro group containing carboxylic acid will be having the highest acidity, then benzoic acid, then comes the alkyl one. Clear? Now, moving on to the next set of reaction, that is reactions involving cleavage of carbon-oxygen-hydrogen bond. That is, again you have RC double bond OH. So, now there is going to be a breakage of this carbon-OH bond. Clear? Now, the formation of anhydride. Carboxylic acids on heating with mineral acids such as H2SO4 and H3PO4, what happens? Or with P2O5 gives corresponding anhydride. Now, what is anhydride? First of all, it can be RCO. So, this is an example of an anhydride, right? So, how it is formed? So, you have taken one molecule of acetic acid here, another molecule of acetic acid here. Now, what is happening? In presence of some mineral acid or P2O5, if you are heating it, what you are going to get is anhydride. Anhydride means what is going to happen here is CH3COO will remain here and the CH3COO will remain here. What will happen? That is going to combine here and an anhydride will be formed and water will be removed from this. So, this is the method of forming anhydride. Now, next one is esterification. Esterification we have already studied in alcohols as well. That is, acids and alcohols combine together to form ester as well as water. So, it is a reversible reaction. We have studied this. Carboxylic acid are esterified with alcohols or phenols in the presence of a mineral acid such as concentrated sulfuric acid or HCl gas as a catalyst. So, you have RCOH and ROH, that is alcohol, in presence of acid, that is sulfuric acid. What you are going to get? Ester and water will be removed. So, you can see RCOOH and OHR dash, that is your alcohol. What is going to happen? H2O is going to be removed, water is going to be removed. So, you will have RCOOR dash, water is going to be removed. So, this is the esterification. So, you will get an ester smell. That is how another test to identify carboxylic acid. Esterification is another test. Another one was sodium bicarbonate test we have already discussed, right? Now, reaction with PCl5, PCl3 and SOCl2. That is, so let's see the reactions with PCl5, PCl3 and SOCl2. The hydroxyl group of carboxylic acid is replaced by chlorine atom when treated with PCl5, PCl3 or SOCl2. In all of this, what are you having? This is chlorine. So what is going to happen is RCOOH. In this, OH is going to be replaced by Cl and you are going to get an acid chloride. That is RCOCl. That is a product you are going to get, and you will have byproducts also based on whether you are taking PCl5, PCl3 or SOCl2. Clear? So thionyl chloride. What is thionyl chloride? SOCl2. It is called as thionyl chloride. Is preferred because the other two products are gaseous and escape the reaction mixture, making the purification easy. So let's understand this. Carboxylic acid, when it reacts with PCl5, you are going to get COCl. That is, H is going to be replaced by Cl. So you will get an acid chloride. What are the byproducts? PCl3 and HCl will be formed. So it is important to remember this byproducts as well. Now if it is reacting with PCl3, you will get, of course, acid chloride and phosphorus acid, that is H3PO3. Now if it is reacting with thionyl chloride, this reaction is important. You are going to get acid chloride, SO2, sulfur dioxide gas and HCl. Both of these are gases and it will escape from the reaction mixture. So it will become easy for the purification of your acid chloride. So compared to the other two reactions, it is this reaction, that is reaction with thionyl chloride, which is preferred because the byproducts are SO2 and HCl, which are both gases, and it becomes easy for the purification. So this is very, very important to remember in your examination point of view as well. So thionyl chloride reaction is preferred. The next one is reaction with ammonia. Carboxylic acid reacts with ammonia to form ammonium salt. First ammonium salt will be formed, which on further heating gives amides. Okay. So what are amides? RCONH2. This is called as amides. So let's see. Acetic acid reacts with ammonia. First, what will be formed? Ammonium salt will be formed. That is, NH3 gets added up to this H and form NH4 plus. So you will have CH3COO minus and NH4 plus. That is the ammonium salt which is formed. Now, when we are heating it, in the next step we are going to heat, water will be removed, H2O will be removed, and you will get the corresponding amide will be obtained. So now we are taking benzoic acid reacts with ammonia. First you are going to get the salt, right? So this NH3 will be added to this H. You will have COO minus and NH4 plus you are going to get. That is this one. Now to this, water will be removed. So what you will get? Again, amide will be obtained. Now another example, on both sides you are having the carboxylic acid. That is on the first and second carbon atom. This is a diol to which ammonia is added. Now what is going to happen? This NH3 is going to be added to here as well as here. So you will get the salt here and here, right? And from both of this, water will be removed and you will get amide on the first as well as the second carbon atom. This is called as phthalimide. Clear? So this is the reaction with ammonia. Moving on to the next one, reduction. Carboxylic acid are reduced to primary alcohols by lithium aluminum hydride, or better with diborane. So lithium aluminum hydride is used as a very good reducing agent which will reduce carboxylic acid directly to primary alcohols. So diborane does not easily reduce functional groups such as ester, nitro, halo, etc. Sodium borohydride does not reduce the carboxyl group. Okay, so you have lithium aluminum hydride which is best for this reaction, and you have diborane also, which is B2H6. Either of this you can use for reducing carboxylic acid to the primary alcohol. So this is a very good reducing agent, and you have diborane which is used for carboxylic acid only. It does not easily reduce the functional groups in nitro, halo, ester, etc. And you have sodium borohydride, that is NaBH4, which does not reduce carboxylic acid to functional group. That is alcohol group, right? So you have carboxylic acid in presence of lithium aluminum hydride or diborane. What is going to happen? Primary alcohol is obtained. Clear? Now the reactions involving the breakage of COOH group itself. Okay. So the first one is decarboxylation. So again, something is going to be removed. What is decarboxylation? We are going to remove carbon dioxide. CO2 is going to be removed. So you can see here, carboxylic acids lose carbon dioxide to form hydrocarbons when their sodium salts are heated with soda lime. What is soda lime? Sodium hydroxide and calcium oxide combined together form soda lime in the ratio 3:1. NaOH 3:1 calcium oxide we have to take. This reaction is known as decarboxylation. So this is very important reaction. You need to know what is the reagent that you are using in decarboxylation. That is soda lime. Now what is soda lime? It's a mixture of sodium hydroxide and calcium oxide, right? So sodium salt of carboxylic acid. We start with that. Sodium salt of carboxylic acid reacts with soda lime. That's a mixture of sodium hydroxide and calcium oxide. What you are going to get? Carbon dioxide will be removed. That is CO2 will be removed. And what will be present? RH will be formed. That is RH. What it is going to be? So it is going to be a hydrocarbon. So let's take an example. CH3COOH I am taking. What is going to happen? It is going to react with NaOH and calcium oxide. So what is going to happen? Carbon dioxide is going to remove. You will get CH3 and the hydrogen. So what it is actually? Methane will be formed, right? And sodium bicarbonate will be present as a byproduct which is obtained from the soda lime that we are using. Now the next one is Kolb's electrolysis. On electrolysis of an aqueous solution of alkali metal salts of carboxylic acid, salts undergo decarboxylation, forming hydrocarbons containing twice the number of carbon atoms present in the alkyl group of acid. So this is also another method in which you can get a hydrocarbon having twice the number of carbon atoms present in the carboxyl group. The next one is halogenation. So this is a very important reaction and is of course a named reaction. Hell-Volhard-Zelinsky reaction. It is also in short form called as HVZ reaction. So this is very important. That is basically halogenation is what is going to take place. So carboxylic acid having an alpha hydrogen. So having alpha hydrogen is important. Are halogenated at the alpha position on treatment with chlorine or bromine in the presence of small amount of red phosphorus to give the alpha halocarboxylic acid. Okay, so what is going to happen? Halogenation is going to take place in the alpha carbon atom. So let's see here, RCH2COOH. So this is the carbon atom containing the functional group. So the adjacent one, this is going to be our alpha carbon. So there is of course a presence of alpha carbon, right? So now let's consider formic acid. HCOH. There is of course no alpha carbon atom here. So this won't undergo this particular reaction, HVZ. So let's see here, alpha carbon. To this alpha carbon, the halogen atom is going to be attached. So either we can add X2, it is shown here, that is chlorine or bromine in presence of red phosphorus. What is going to happen? The halogen is going to be added. That is the chlorine or bromine is going to be added to the alpha carbon atom. So this is called as HVZ reaction or Hell-Volhard-Zelinsky reaction. Now moving on to the next one, that is ring substitution. Aromatic carboxylic acids undergo electrophilic substitution reactions in which the carboxyl group acts as a deactivating and meta-directing group. Okay, so carboxylic acids are meta-directing group. They do not undergo Friedel-Crafts reaction because the carboxyl group is deactivating and the catalyst aluminum chloride gets bonded to the carboxyl group. So they do not undergo Friedel-Crafts alkylation or acylation because of the presence of carboxyl group and they are deactivating, hence they direct the incoming electrophile towards the meta position. Okay, so you have benzoic acid. First we are going to nitrate it. So we will use nitrating mixture, that is concentrated nitric acid and concentrated sulfuric acid. Nitro group will be added in the meta position, right? So this will be added in the meta position. Now you have carboxylic acid, that is which one it is? Again benzoic acid. The halogen is going to be added, that will be also added to the meta position. So what you have to remember, carboxylic acids are meta directing groups. Clear? So now moving on to the last part, that is different uses of carboxylic acid. Methanoic acid is used in rubber, textile, dyeing, leather and electroplating industries. Now ethanoic acid as a solvent, as in vinegar in food industry. So what is the acid present in vinegar? It is ethanoic acid or acetic acid, right? Hexanoic acid is used in the manufacture of nylon 6,6. Now higher fatty acids, that which is having more number of carbon atoms for the manufacture of soaps and detergents. And you have esters of benzoic acid which is used in perfumery. Esters, of course, it has a very good fragrance that is used in preparing perfumes. And sodium benzoate, it's used as a food preservative. So these are few uses of the substances, that is different carboxylic acid, which we have studied now. So by this we come to an end to this chapter, aldehydes, ketones and carboxylic acid. So this is a very important chapter and it is one of the most important chapter in organic chemistry. So I hope the concepts that I've covered in this chapter is clear for you. So in the next session, let's meet with a new chapter. So that's all for today. Thank you.